Okay, so let's continue on our journey in the backpropagation and the brain paper. And the key idea is to get rid of backpropagation and come up with a new kind of learning algorithm. And the last video was very confusing because it was not clear what I was saying. So I ended up deriving all the equations from my own side, and then that is what I am going to be presenting. And we will not be focusing on the paper, but on the key takeaways of the paper and how you can build such a learning algorithm step by step. So let's first discuss like what's the key job of a learning algorithm. So in this case, like what you have is like you have an output neuron I. So this is a neuron I, and it is connected to like some neurons in the layer before it. So in this case, it is connected to a neuron at layer J. It's connected to a neuron J and J dash at the same layer. And the idea is that on this connection there is a weight. So there is a weight Wij and there is a weight Wij dash. Ij means that the connection is between I and J, and similarly the connection between J dash is basically what the connection between I and J dash. So now the key point is that if you change any of these weights Wij, if you fluctuate like any of the Wij, it will actually have an impact on like what is the input to the neuron, which is like Xi, and then that will also govern like what's the output Yi, which in turn will govern like what loss your network is. So you compare like the loss of the network with your ground truth target, and your aim is actually to wiggle the weight in the correct direction. You have to wiggle this weight so that like it makes like a low error. So the aim of a learning algorithm in this case is to estimate like how much change do you need to make to the weight in order to lower the error, and that's basically known as del of loss with respect to Wij. But in this case, like if you look at this graph, this computation graph, you can actually calculate like del of L by del of Wij by doing like a chain rule. So del L by Wij is basically what happens to the loss when you wiggle the Y, and then what happens to Y if you wiggle the X, and then what happens to X if you wiggle the weight. And this is like the a standard expression which can be written as a product of like three derivatives: del L by del Yi by del Xi, and del Xi by del Wij. So now the key point here to understand is that if you look at like the first term, this whole term in blue, this is actually known as the error signal at layer I. So and this is like pretty simple. So del L by del Yi will be del L by del Yi, and del Yi by del Xi is nothing but f dash Xi. So what this means is that in case like let's say your neuron is I, and it is like given by a function f. So you have like Xi going in and Yi coming out. So, and let's say that your f is basically your Y is equal to f of x is equal to Xi squared. So then del Y by del X is 2 times X to Xi. So this is like your f dash Xi is going to be 2 times Xi. So to know like the derivative f dash Xi, you need to actually know beforehand what is the function f which your neural network is modeling, which in this case is Xi squared, and then you need a mechanism to actually take the derivative, which in this case is 2Xi, and then that's how like you get the derivative. So now the key point is that you compute this derivative, and it requires you to know this f dash in advance. And then the final part of the expression is basically how does the input activity change if you fluctuate the weight. And so what you can imagine is that let's say that so your total input, which is to the ith neuron, is gonna be given as like the sum of input which comes from J and J dash. So in this case, Xi is basically Wij Yj plus Wij dash Yj dash, which is basically like this neuron is outputting a activity Yj, and this neuron is outputting a vector Yj dash. So then this is like the total input which goes to the neuron, and then you can easily take like the derivative of this. So del Xi by del Wij will basically become Wij, and this whole part of the expression, this whole thing will cancel out and become 0, because we are only computing the change of Xi with respect to Wij, and we are not, and at that time like basically the Wi dash j is gonna remain constant. So the key point is that after like you have done this whole derivation, you can imagine that you have like the amount of weight change which you make is basically the learning rate times the error signal and then the incoming activity at that neuron. So from like the perspective of like a neuron, what it means is that you have a neuron I and you want to update like the weight wij, and there is a input activity, like there is like yj which comes as input, and then there is like yi which comes at output, and then there is like a error signal here del I. So you can multiply this error signal by actually taking like you can actually compute like the weight update on this particular part of the connection by multiplying this by multiplying this error signal with the incoming activity, and that is like pretty much it. So that's how like the standard, and you can assume that this neuron I is basically the neuron across any of the layers of the neural network. So if you have like 1 2 3 and so on till 100 layers, then in that case this neuron I will be present at that layer. Okay, so now the key point is like, let us analyze like the key point in backpropagation. The standard problem in backpropagation is actually appearing when you have to compute this part of it. So the gradient of weight has actually contains like this part del I, which is known as error signal, and this is like the main culprit. So let's assume, so basically what you do in like a standard backpropagation. So you can see that this expression depends on two things. It depends on xi, it depends on f dash, and it depends on yi. So what backpropagation assumes is that, okay, let's store xi in the memory, let's store yi in the memory, and we know like the precise mathematical expression of y equal to fx, and they assume like that this y this f is known, and then you can easily compute the derivative. So they know the mathematical expression for f dash, and that's how like the derivative can be computed. And then what you can do is like, once you know this f dash, you can easily feed this xi to f dash to get f dash xi, and that will give you like this expression. And that's like how the key point works. So in this case, like the problem appears in two ways. So there are like two bottlenecks which you see here. So the first bottleneck is that you need to know like the f dash in advance. So you need to know the precise mathematical function which is the derivative of each neuron. It is not clear whether the brain computes these explicit derivatives. So there should be a way to compute like this kind of f dash, or like there should be a way to compute this del I which does not depend on taking the derivative at all. And that's the whole idea which I am about to discuss, that you need not know like this f dash function in advance to calculate this del, and it's a very clever workaround which we will discuss. And the other point is that in this case, like let's say you have like 5-layer neural network, okay, and then you passed in your activity xi, and you got h1, h2, h3 and h4 as the input. So in this case, like while you are updating all the layers in a backward pass, so let's say you update layer 4 again, layer 4 first, and then you update layer 3, and then you update layer 2, and then you update layer 1. So like the way the signal propagation will look like is basically, first you will calculate like the error here, del 4, the error signal here, and then you will calculate like the error signal here, then you will calculate the error signal here, and then here, and so on. And when you have to compute like the weight changes of this particular weight, what you will have to do is you will have to actually multiply this del 4 by h4, and then similarly you will have to multiply del 3 by h3 and del 2 by h2 and then del 1 by h1. So to be able to like do this job, to be able to get this value, it means that you need to store h1, h2, h3 and h4 in the memory of your computer when you have made a forward pass. So let's say that you have 4 such layers. So there will be 4 separate activations which your network computes, and that will occupy like a certain amount of memory, which is like gonna be double, or it's going to be like very large. So the key point is like when you are making a forward pass, you are still storing like the intermediate activities h1, h2, h3, h4, and then on the backward pass, since you're computing like these extra activities, it's gonna take a lot of extra memory. And similarly, when you're making a backward pass, you also have to compute like this delta signal, which is like this delta. So at a particular time, like once your forward pass is computed, like you are storing like the input xi, you are storing like h1, h2, h3, h4, and also you are actually computing another kind of signal which is known as the gradient signal. And that gradient signal is basically what you say is del 1, del 2, del 3 and del 4. So there are like these different kind of signals, and turns out like all of this is a waste of memory, and it's just needed to like the optimize the weights. So if we can come up with another way in which we can calculate this del I, and we don't have to like require any of this memory which is occupied by standard backpropagation, then we are doing a pretty good thing, and that would result in a learning algorithm which is really good for edge devices. So let me talk about what that learning algorithm will be on the next slide.